So yesterday we talked about cross-validation, which is dividing the data set into training and testing, and also dividing the whole into 5 folds, for example. It can be even more, 10, but 5 is basically what we do in practice, because we usually take 20% to 80% between training and testing data sets. Of course, if you have a different percentage, you may choose different type of folds, okay? But in the case where you take 20% to 80%, we can divide into 5 folds, and then each time we're going to change the fold in order to change, swap between the training and the testing data to explore different space. And today I'm going to make you an illustration through Python code about how we can do this in practice. And the objective again is to find an unbiased estimation of the generalization risk. We want to find what is the most appropriate value that will represent the general loss. Okay, and usually capture this using the average or the mean and the variance. And we want the variance to be as small as possible to have strong confidence that this represents the population or the unbiased estimation of the generalization risk. So another thing that we do in practice is that we don't only divide the data into train and test only, but we try to divide it into train, validation, and testing. So what is the difference between validation and testing? What could be the reason between validation and testing? Any thought? So the validation, it's a part of the data set that we use during the training, but it is not used for training. It is used for what? It is used for testing or validating the current model while it is training. What is the purpose? So you can think about this orange line as validation. So usually when we train a model, we're going to have a training loss. So for example, I trained for 10 epochs. I will measure the training loss, okay? And I can measure also the validation loss at the same time. And the validation, it means if I take all the pictures in the validation data set and make inference, I will have an error. So this error will be the validation. So this helps us to observe the difference or the variance between the train data, the train loss and the validation loss. If it is very high, I can know in advance while training that there could be an overfitting. Okay? Before going later on to the testing. So if the validation is already very far from the training, I don't need even to test it on the test data set. It means there is something wrong in the training itself. Maybe there is an overfitting. So we can use this as a reference about how general my model is. Does it make sense? Okay, while training, so I'm not going to use this to optimize the weights. I'm going to use them to make inference on a temporary model and check what is the current loss for unseen data, for an unseen data. Yes?
Validation test on unseen data.
It's unseen data, yeah. So the training data will be used to update the weights of the model using the gradient descent, using optimization techniques. We will use the training to update the weight of the model so that we reduce the loss with respect to the training data. Okay? And the validation data will not be used to optimize the model. It will be used to test the model during the training. And this helped me to visualize the difference between the loss of the data that is used in training and the loss of a data that is not used in the training. And this helped me to understand early in advance if there is a possible problem of overfitting. And overfitting means the data fits mostly the training, but it's not general enough for unseen data. Okay? And we talked about this yesterday, about the problem of overfitting and the high variance and the low variance and high bias as well, when the model is simplistic like this. Yes?
If we get overfitting model, why don't we just manipulate the weights or the biases a little bit so we can generalize them?
What do you want to do?
When we get overfitting, يعني ايش ممكن نغير شوي بالويتس بالبايس بدل ما نعيد.
Yes, we are actually, the optimization process is something that we didn't talk about. The optimization process at each iteration, I'm going to update the weight and the biases of the model. For example, you have a simple linear model, W1 x plus b. So every iteration I will change the value of w and b such that I reduce the loss. But I will reduce the loss with respect to what? To the training data, not to the validation. You see what I mean? Okay. So the validation, okay, it represents a subset of the data set used to tune the model parameters and select the best performing model to check the variance between the loss in the training data set and also in the validation data set. Now, if I made different models and at the end I find a model where the validation and the training loss are close to each other. So it's likely that this is a good model. Now I'm going to take the same model and test it with what? With the test data set, another reference. Now, if the test data set also is very close to both, I can see it's possible that I have now a general model. If I find that the second reference, which is the test data set, is still high, okay, because it has captured a different distribution from the validation and the testing, maybe I need to train another model. Okay, it's all a matter of distribution. Look, the training will have a certain data distribution, which will be picked randomly from the sample. The validation will have a different distribution, and the test will have a different distribution. So if I have an agreement among 3 different distributions that my model converge to a particular loss, I can say that this is very similar to the generalization loss. Of course, it's still possible you have the training validation test work together, but you want to try it outside and it fails because the new distribution of data is not modeled as part of this one. And this is why we do cross-validation. It's basically to try to pick up different type of distributions during the training, okay, to make sure that we try to capture as much pattern as possible during the training, yes.
If our model is still not accurate after training, validation, testing, so how can we deal with that?
Maybe your model is not correct, it's wrong, you have to change the model, you have to increase the size, you have to bring more data. So there are many ways on how we can act, yes. Maybe your model is too simplistic, or your model is very complex, or you need to change completely the model. You're using linear or polynomial regression, you need to use a neural network or to use a different technique to capture the patterns. Okay, so it's
possible to improve the model without getting more data.
Yes. Okay, so there are parametric models like linear regression, polynomial regression, and there are non-parametric, which are more general and can capture complex patterns. Like, for example, we use convolutional neural network to capture the pattern inside an image. We use recurrent neural network to capture the patterns inside a text or a sequence. And now we use transformer to capture both in sequences and also, or not sequences, in text as a full context plan, or also in images, considering them as patches. So these are different architectures of different models, and each of them try to capture the pattern in a much better way than the others. Okay. So always in practice, we need to divide our data into training, dev, or validation. Sometimes we call it the dev because it's during the development, and another one is the test split. Okay. So there is no a single rule on how to do that. It can be 60%, 20-20, this is 20%, can be 98%, 1%, 1%, depending on the size of your data. But typically it can be 80%, 10%, 10% also. Alaikum salam wa rahmatullah. Okay, so this is applicable in different domains, like also in computer vision. Now imagine that you train your model into high resolution images, and then you make an inference on low resolution image. So this image and this image will have completely different distributions. Okay, and it's pretty much similar to the case that we have here in regression. Okay, if you change your sample from different regions, you may end up with completely different models. So I hope now the idea of it's all about capturing all the patterns in any distribution. The distribution must be general enough. And this is why we want to have a large data set. When you have a large data set, it's likely you didn't miss any pattern into all possible patterns. Okay? Now, imagine that you want to train a computer vision algorithm or network, and you have collected 100,000 images from the web, and this is what you usually do, okay? And you have only 8,000 images that you collected from your target distribution. For example, in one of our project, we wanted to make a model that will provide classification of the vehicle type or the vehicle brand. So what we did, we collected images from the internet. And then the model didn't work as expected when we took picture here from PSU and we tried to apply on that model. Okay, so the picture that we collected from PSU, for example, are called target distributions. Okay, because it's collected from the environment where we will deploy the model. So how are you going to distribute your data here in training, development, and testing? Are you going to put only the 1000K images in training and this in testing, or the opposite, you will put all the 8K images in training and then you test on these ones? How are you going to make distribution?
I think I will put some of the 8K in the training, and then
Some, yeah, what does it mean some?
so it can
1%, 2%, 20%?
maybe 30%.
95% from the images and about
Yeah.
50% from the web, 95% and 50%.
No, you have train, dev, and test. What's the distribution here?
Okay, will dev will
Yeah, there are many options. Now, the first option, I will take random, shuffle. Shuffle images all together and just pick random. That's one of the possible ways. Okay? So it's like having, but this training will be more for generalization and probably less optimal for my target distribution. واضح? Because I'm going to shuffle. Another way is to do like this. Put all the 100K, this is like data augmentation. Take half of the pictures, put them in the training, and dev and test will be only for my target distribution. So here in this case, whatever training loss I'm going to have, I'm going to test the final product with respect to the unseen data, because later on I'm going to deploy it outside. Okay, I'm going to deploy it into my target distribution. So this is the better option, is to put half of the pictures in the dev and the test. So the dev and the test will be 100% pictures from from the target distribution, and then we'll take the other 50%, put it here in the training. Okay, that's also an option, yes. 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 So it will be part of the target distribution here. Now, when you test, why this is better? Because later on, when you're going to calculate the validation loss and the test loss, it will give you the real estimate of your model when deployed into your target environment. Okay? Even if it is low resolution, high error, you will know this in advance. You will not be surprised later on when you deploy your model. Okay.
What will happen if we train it only using the target distribution?
You will have small amount of data. So if your network is very large, you will have an issue of underfitting. Okay?
It's based on the accuracy relative to the target
Yes.
distribution.
If you have, for example, a model so that is large and you provide small amount of data, it's not going to converge. Okay? And if you make a simplistic model, maybe it will not capture all the features. So this is why usually we try to bring data, and this is what we call data augmentation. So data augmentation, I can take also pictures from my target distribution and make transformation, or rotate a little bit, add some brightness, make some contrast, do different type of changes. So this is good and bad, because it may provide me more pictures or data within my distribution, but I can lose generalization as well. Okay, so there is no rule of thumb, but it's kind of common sense on how we want to tune your model, yes.
بس يعني انت اصلا لما تحط 50% من الايمجز ان ديف تيست بتوع والباقي يعني ما بكفي 50% يعني يكون بس يعني بس
ما معنى 50%؟
50%
Of what?
of the target distribution in the training just
احنا we took 50%, yes.
is it enough in the training?
We don't have options, unless if you want to change, you want to make less. If you want to make only 1,000 images in dev and 1,000 images in test, so you can add 2K here. That's also possible. But of course, if you reduce the number of images in the development and the testing, maybe you will not test all the possible situations. I don't say that this is wrong. We don't have an explicit problem. Now, depending on the type of problem, yes, I may also, in some of the cases, we took only 200 images for the dev and 200 images for the test. If I consider that, this is sufficient. Okay? So if I have a lot of data, I can use, for example, 200 pictures or 500 pictures or 1,000 pictures, one in the dev and another set in the test. Okay? It's matter. But, this is just to illustrate that instead of shuffling, now the bottom line here is that we will put the dev dataset and the test dataset, all of them from the target distribution. Now the number depends on the size of your data. Does it make sense? Okay. So we talked about the bias and the variance trade-off. These are just other slides. Okay, and this slide actually explains the difference. Look now, this is really important. You have a model complexity. So we have observed here, we can have complex models that have high variance and simple models that have high bias. So what happens here? If you have a complex model, usually the variance will have a tendency to be high and the bias will be small. If you have a low complex, a model that is simplistic, in this case, the bias will be high and the variance will be low. Okay, so this position here now, this is the optimal here. We want to be in this optimal, minimizing both the variance and the bias. So the best model would be the one that is in the intersection, okay, of the error. And this region will be considered as an overfitting zone because it will have low bias and high variance. And this region will be considered as underfitting zone because of we have high bias and low variance.
Doctor, why was the optimal model not exactly at the intersection? What was it before?
Well, yeah, the optimal model, it's the one that will try to reduce both at the same time. Okay? This is theoretical. Okay, theoretically, I need to find the minimum point in the intersection of optimal model complexity with reducing the error, reducing both the bias, because, the error is basically, look, it's the bias square plus the variance plus irreducible error. There is an irreducible error. Look, the model will never be equal to 0. And this depends from the noise, this depends from other parameters outside of the model itself. Okay? It's basically captured by the irreducible model or the irreducible error is captured by the data itself, the bias of or the noise, probably the randomness and unknown factor from the data. Okay, and we have seen now in linear regression you cannot have a perfect line here, so there is still an error that you cannot manage. If you make infinite number of models, you will never reach 0. Okay, so this irreducible error is like it's from unknown factors that will always be there. Okay, and will capture the error. So this is the summary of the errors that you can have: the bias square, the variance. And you can see now the bias must be square because the variance is actually also the square of the standard deviation, okay, plus an irreducible error. And now, based on the outcome of your training, you can decide what's the issue. Now, imagine that you have a training error of 1% and a testing error of 11%. So this means I have high variance, I have overfitting, very low training error, and high testing error. Now, if you have 50%, 16%, both of them are high. So here, I will have high bias, okay? And this is underfitting. So both of them are high here, okay? And if you have 15% and 30%, you have high bias and high variance, both together. So this model doesn't fit at all.
Is it too simplistic?
Huh?
Is it too simplistic?
It's a wrong model because both the training and the testing are, yeah. Now, what I see when I have underfitting is when you have a test accuracy. For example, I probably need to change this one. If I have, for example, 15% in training and 5% in testing, or 6% in testing, not 16. Okay, consider this as 6. Now I have underfitting. Okay, and if both of them are low, so I have low variance and low bias, and this is a good fitting model. This is how we interpret the values of the bias and the variance cases. So this notebook is going to show you the impact of cross-validation, how we do cross-validation in practice. So first of all, we're going to start the same simplistic model about linear regression, where we're going to create a data set, okay, with 200 samples, with a noise and a random state. So create a data set, make regression, and we will put the data set into a data frame. So it's going to create random samples, 200 samples with a certain noise, okay, and this is the noise, the number of feature. It's only one feature. You have a feature X, it will give you a prediction of Y. It's like you have, for example, the number of rooms in a house and the price prediction. Okay, it's 1-to-1. Yeah. The second method, so I have a couple of methods. It's data exploration and visualization. So my objective is after we generate the data, you will be able to visualize it as histograms. And let me go here, to explain this. So I start by creating a data, 200 samples. This is the mean of X, this is the mean of Y. And here you can find the distribution of, this is the data itself. This is the distribution of X, which is the feature. And this is the distribution of Y. Okay? Look at this. We generated random X, random Y. It provides us something close to linear regression. And you want to find a model right now. And this is how the data is distributed around X, and this is how it is distributed around Y. Now, in order to create a consistent model, we thought that we need to do a cross-validation. So what is the objective of cross-validation? Dividing the whole data set into faults, and then doing the testing into different faults. Yes. So for this, there is a method in scikit-learn, which I imported from here, k-fault. Okay, which will do the job for us. Okay, we take the k faults here, and then we visualize the fault and their distributions. Look now, I divided into 5 faults. Now this is the first one. Fault 1, feature distribution. So this is the distribution of X that I will use for training, and this is the distribution of X that I will use for validation. So the blue data will be used for training to optimize the weights, to converge. And this pink data will be used for what? For validation, for making inference and checking the error that you will get. And this one is for the Y, it's for the target value. And look, this distribution of data that I will use to build a model is different from this one. So this will be a second model. Okay, and this will be a third model. Look, completely different. Okay, here there is a peak here, and now there is a peak into smaller values. So the distribution will be different. What's the objective? I can check over different configurations whether I can converge to a certain general loss, and this helps to have general model that we can build. واضحة الفكرة؟ Okay. So this is how we divide into 5 faults.
The y-axis is only the frequency, right?
Yes. Now we train the model. It will be trained for the different faults. We provide df and the k faults. Of course, there are the functions already defined there. And we can observe now cross-validation results. Look at this. This is fault 1, 2, 3, 5, 4, and 5. Okay, so in the first iteration, we find a training MSE. Now, this is the first configuration, the first distribution, then the second distribution, third distribution, and so on. Look at the values. The MSE is here 399. The validation is bigger. Okay, look here, it's different. Now, if you see this one, you can say probably I have a little bit of overfitting. But if I make on a second distribution, it's the opposite, right? Okay, and these are the parameters, the weight and the bias, okay, W and B. Look, here we have also a different value, a different value, a different value. Now, taking all of this, we analyze average result, the train MSE. So we take the fault 3. Where is fault 3? We take the average result, train MSE is 405, the validation. So this will be the average of all the faults. And this will be also the estimated parameters that we take in average. Standard deviations. So there is 1.5 deviation between the faults. So this provides us a better understanding about how our model is general. Okay. Okay. This is the train MSE standard deviation 16. The validation MSE is 65. Now it's like a warning. Okay, our model work best for the training more. There is a big variance in the validation. So, if I'm going to take this model into the target deployment, I will be a little bit skeptical that it's not going to work very likely as expected, because it's not only that we have here close average values, but this standard deviation also is kind of warning. There is a big deviation. Maybe I need to make more training in order to find better convergence. Yes?
If we repeat the k-fold distribution, it will yield different results or still the same?
Yes. I mean, if you change, it's going to lead different results.
So it's randomized.
Yes. But at the end, when you have multiple results, you can have better confidence about. So what matters about the confidence is the standard deviation. I mean, I feel more comfortable now for the training, but less for the validation. Although here, I don't have too much difference. Okay? I don't have too much difference.
So جماعة فهمت الحين ايش الفرق بين training data وvalidation data؟ هذه الديفلوبمنت هذيك الافضل development.
شوف الآن خلينا نشوف التريننج كيف يصير. ممتاز. سؤال جيد. Let's see during the training. Look, model.feed is the instruction to train the model. What did you use here? X-train. هل في validation في التريننج؟ ما في. وين الvalidation? Predict. So I will predict, and then I'm going to use the prediction to calculate the error, both for training and for validation. So the validation is not part of the model training, but it is part, it's only part of the prediction. Prediction doesn't make any optimization. It's here where I optimize my model.
والtraining data تجي من المود نفسه سوينا له train، بس الفاليديشن من الاساس اللي سوينا عليه train صح؟ يعني من الفاليوز الاساسيه اللي عندنا.
Validation, yes, it's our data set. Look, what do we have في validation data set? You have feature and the correct prediction, صح ولا لا؟ تخيل مثلا you have a validation data set with 10 items. For every feature, it's prediction. Okay? In these 10 predictions, I have 8 correct and 2 wrong. So I have a loss of 20%. واضح? This is how we calculate it. So when I make prediction, is to calculate the difference between the ground truth and I will calculate the MSE between the ground truth values and the predicted values. And this is how we calculate the validation loss. So the validation will not be part of the model optimization. So here we have calculation of the derivative, changing the values of the weights, optimizing the model. It's all with the training data. We will see this in convex optimization still, okay? It's based on derivative. مش كلامنا قلنا derivative, we want the derivative of the loss equal to 0. Yeah, we're going to apply, this is applied here in model.fit. But this derivative of the loss will be only affected by what? The training data, not the validation. So the validation will be used to use that model. Look, now I predicted a model, or I developed a model, I will use to predict the loss or the error. And then it will be stored here for later statistics. Yes?
Validation concept development?
Yeah, we call it dev or validation. It's the same. The testing when? It's after to calculate all the models. واضح الحين؟ I will give you this one. Look, later on at home you can play with the dataset size. شفتوا الآن في discrepancy. جربوا كبروا dataset size 10,000. And look at the standard deviation. Look at the average. You will see that they'll become closer. Okay? Now because you have only 200 and still we make different faults, so 50, 50, 50 in each. Okay? Of course, this variation is expected. But try to have, for example, 1,000, 2,000, 5,000 values in the data set, and you will see that the convergence will be much better. Okay, look now, we got all these values, and this is the visualization of the prediction. Look, this is the model for fold 1. They are close, visually they are close. I mean, there is no big discrepancy here between the different folds. Maybe if we zoom more, there is a variation over the different models. Now, just to finish, this is another code that will calculate the generalization risk among all of them. Now, if you run this code, here we can visualize the training set size over the mean square error. Okay, so this is during training. This is the variation of the training error in blue, and this is the variation of the validation error in red. And what is here in this area here, like this, in the shaded area? This is the variance. Okay, so you can see the variance in the training is smaller than the variance in validation. Okay, so this is the during training the first 500 values, 100 values, 50, until 250 number of epochs here. Here analyzing the prediction variance. Okay, the prediction variance is shown by this shaded area. It's small. So all these models, they have low variance, so I can say that I have more confidence into my my training. This is the distribution of the generalization gap or generalization error. Okay, and this is the train versus validation error. So these are different statistics just for you to get more feeling about the issues that we face in training between validation and testing. And the main lesson that we want to have is that when you train a model, to say that your model is general enough, you must have small training error and also small testing and validation error. This is how you can at least think that your model could be general enough. And of course, later on when you deploy it, you need to monitor whether there are some possible